So physics part 2. You've got this container, you've got a fluid in it. But instead of calculating how much force is on the face, now you want to pump the fluid out of the container. Just like before, I would like to identify what the key variables are to how much force or how much work is done in pumping fluids out. So consider these 3 or 4 cases. Here's a normal case. That person is sucking fluid out of a cube. By cube, because it's easier than a cylinder. This person 2, is this person going to have to do more work or less work if they suck out the fluids from this really long straw? More work, okay? What about this person who's sucking out, I'm not sure why I went with mud. I was thinking maybe more milkshake or something. That's weird. I don't know what I was thinking. No, I don't know what I was thinking of. Let's go milkshake, a really thick milkshake. Will that person be doing more or less work? More work, okay? And this person, who's not so much with a cube, but this really long trough. They're sucking fluid out of a trough. More work or less work? More work. All right, so then, based on this, the 3 variables that affect how much work you do in pumping a fluid out of a container are, what's this one? What is it? Length or distance. The distance you have to pump the fluid. If you have to pump the fluid out of a really long tube or something, that's more work. What about this guy? The weight density, yeah. The density of the fluid matters. The more dense, the more work. And what about this guy? Not so much area anymore. What differs, these have the same area of the front face. What differs is the volume now. Not so much about area. Now it's about volume. The more volume, the more work. Now all these are directly related. So mathematically speaking, it's going to be a direct relationship, so a multiplication relationship. I guess that's what I meant to say here. So the work is going to be lots of little calculations of distance, density, and volume. Question then is, why calculus? Well, this slice here, it's all about the distance. Varies. You're not pumping the same distance everywhere. This level of fluid, for example, needs to be moved further than this if it's going to be moved out of the top, and that's the problem we'll be working with, is when it's sucked out of the top of the container. The distance varies, and so we'll need to, because of that, we'll need to sum many work calculations. All right, so it'll be an integral, and work will be the sum of many row, distance, volume. I don't want to use D because I don't want you to think it's the same as depth, like in force. It's about distance. So there'll be a slight difference here. Same with volume and area. All right, so let's see what a case or 2 looks like. Rectangular prism with an 8 by 6 by 10 is filled half filled with water. How much work is required to pump the fluid out of the top edge? Let's start by drawing it. The base is 8 by 6. The height, it is 10 centimeters. Centimeters? Maybe we shouldn't get funky with the units. Will you scratch those and call these meters right now? I don't want to get into funny business with the units yet. We'll build up to it, but let's just go basic. So it's a big container. All right. It's half filled, though, with water, so it's only filled up to the 5 level. You follow? And you're going to pump the fluid up and out over the top edge until it's empty. You got it? Question is, how much work would that require? All right. So, question, first and foremost, we need to get some variables and define our origin. Let's put our origin right here. So we're looking at first quadrant, okay? This is the x-axis, this is the y-axis. So work, we said, is the sum of many row, distance, volumes. Because it's water, what's rho? Are you starting to have that memorized? Not that I'll require you to memorize it. 9,800. All right. Let's start then talking about distance. Imagine this slice of water, or this sheet of water at 1 meter high. How high or how far will you have to pump it to get it over the top edge and out? 9, okay. What about this one at 2? How far will you have to pump it to get it over the top edge and out? 8. So it seems like every time you're taking the distance as the top level of 10 or the upper of 10 and subtracting it whatever the y level it's at, yeah? So what do you reckon the distance expression is? 10 minus 1. Okay? Now notice here that that 10 is the top of the container, not the surface of the fluid, not the surface of the liquid. All right? You might say, what about the 5? Where does it come in? And it'll come in a second. What about the volume? Now, I'm talking again, not the volume of the whole thing, but the volume of each of these little sheets. So what's the volume of each of those? 8 by 6 by dy. Okay? And the limits of integration. 0 to 5 or 0 to 10? 0 to 5. You're only pumping out fluid, and so the limits of integration are where the fluid is. I don't care about pumping fluid out of the upper 5 meters. That's a non-issue. Let's last but not least talk about units. The weight density is newtons per cubic meter. The distance units, what are they? Meters. The volume units, what are they? Meters cubed. Altogether then, it's Newton meters, which is joules. Work is joules. So when you get your answer, it is in joules. I assume you can calculate that. You'll be able to use your calculator on these. I want to focus on the concept, not the integration is usually pretty straight. Okay? Questions so far? All right. This was an easy case because there's no variation in the slices. The slices are always 8 by 60 wide. That's an easy case. A harder case is when there's a little variation. All right? So you've got a trough here, and it's filled to a height of 2 meters. That's in here. I don't know if you can see that in your picture, but this is 2 meters here. Okay? The weight density is given. Find the work done to pump the fluid out of a small hole in the container. So it's like there's a little hole here, and you're pumping it out and over the top edge. Okay? So let's start with drawing the picture. I beg you, when you have a circle problem, please put the center of the circle at the origin. Even if it doesn't make first quadrant. I know I said you'd like to have first quadrant, but for circle problems, you definitely want the center at the origin. It says here this top edge is 8, so that means it's going to go from 4 to -4, and the bottom minimum will also be negative. It's 2 meters high, so the fluid goes up to a level of -2. And then this will come into play a little bit, but this is 12 meters. All right. So here we go. Put down the old formula. The more you read it, the more you remember it. Rho, distance, volume. What's rho? Rho represents the weight density. In this case, it's given as 8,000. It's a constant. It'll always be given. Distance. So the distance you're going to pump each slice, so you're going to take this slice of water and pump it out, not to the surface of the fluid, but to the top of the container. Using an upper minus lower general idea, what's the distance you have to pump each slice? 0 minus y. I heard somebody say 0 is the upper point, and y is the varying location of each slice. All right? The volume. Now, this is where I start to see, okay, so it's pi or, no. If you have pi in there, you don't know what you're doing. It's not pi. You're talking about the volume of this slice. That's a rectangular prism. I know it's got a circle thing going on, and we'll use that, but you're pumping the volume of this slice, this rectangular sheet up and out. And you have to do lots of those because all these sheets have different volumes. So when I say volume, that's the volume of a rectangular prism stuff. All right? Now what's the width of each one? Is it constant or varying, the width of these? Varying, okay? And is it x or 2x? 2x. I'll have to deal with that in a minute, but for now I'm going to put it down, 2x. What about the length? That's 12, it's constant. And what about the height of each sheet? 2y. All right, so cool. I'll come back to that x in a minute. What are the limits of integration? -4 to -2. All right. Now, 8,000 is cool. I'm going to pull the 2 out front. I'm going to pull the 12 out front. -4 to -2 limits are good. 0 minus y, I'm going to change to -y. Now then, the x is the problem. X needs to be put in y terms. X is always some distance, but it's always some distance tied to on the curve. So you can use, to sub for x, use the equation of the circle. That's where the circle comes in. You knew it had to come in there eventually, and there's where it comes in. What's the equation of the circle? X squared plus y squared equals 4. X then is plus or minus. Now I don't have to sweat plus or minus because I can just use the right side. The 2 takes care of the doubling right and left. So don't worry about the plus or minus if you think more about that. It's not an issue. Oops, that's y. So x is the square root of 4 minus y squared. You follow? You reckon? I don't. All right. So -y times, keep doing that, 4 minus the square root of 4 minus, yes? Instead of 16? Aha, Esther, I didn't get you. Way to go. You're the only one paying attention. Good job. It's not 4 because the radius is 4 squared, or the radius is 4, so it should be squared, so this should be 16. Am I right? See, I didn't get you. I got the rest of these fools, but not you, Esther. Way to go. Okay. Or I just made it. What did you, then, if you plug that in your calculator, you can see this. If I had you do this by hand, it would require you sub-skill, but you can do this by calculator. The units would be joules. I assume you can put that in your calculator. Okay, just be careful. And remember the units for worker tools. You follow on that? Okay? Getting a little, let's pause for a second then, and let's, at this point you've seen a couple, and it's time to get straight in your head the difference between the two, because it's always the case that people get the two mixed up. So in force, it's rho dA, where rho is a constant weight density. D stands for depth, and depth is upper minus lower, where the upper is the surface of the fluid, not the top of the container, minus y. And A is the area of each slice. Usually the height is, not usually, always, the height is dy for each rectangle. Okay, you follow? The base could be constant, like a rectangular prism. It could be varying x or 2x, depending on their symmetry, but that's force. The limits of integration, the limits are fluid levels. They're not of the container. The lower the fluid, the higher the fluid. For work, its rho distance volume, the limits are still fluid levels, not container levels. You're still saying, where is the fluid I'm pumping out? The containers are non-issue, right? The rho is a constant. D, this is distance. This is the top of the container minus y, not the top of the fluid minus y. You're not just pumping the fluid to the surface of the fluid and then dropping it. You're talking about pumping it to the top of the container and over. The volume then is usually, this is usually like the area, but with a length thrown in as well, like the length of the trough or something, okay? All right, now let's get back to a case or two. A trough with a triangular face, top edge 3 meters, side 4 meters, and distance between the bases of 7 meters. The bases of the congruent figures. Is filled halfway up. That's a curtain with gasoline. Find the force exerts on the face. All right. Now, do you agree that if I put the origin here, then I'm going to have second quadrant action? Yeah? Is there any reason I can't just flip it over and draw it that way? So I would suggest, rather than deal with negative x's or bad equations, just flip it over. It's the same work either way. This is 4, this is 3, and that's 7. Boom. Will you tell them they have 25 minutes, please, Chance? Thanks. All right. Where am I at? So, are you done? And the halfway up is crucial. It's only filled up to the 2 meter mark. We cool? All righty then. I'll assume that's great. Would you give this a go and see if you can figure out how much work it would take to pump it out and over the top edge? How we doing? Good? What'd you say for the distance? What? 4 minus y. I'm down. Okay? The volume. If for volume, they said, you saw somebody that said, oh, so I need the base times height divided by 2 times 7. Would you say they know what they're doing? They do not know what they're doing. It's not about the area of this triangle. It's the area of volume, rather, of each of these slices or sheets. All right. So the width, constant or varying? Varying. 1x or 2x? 1x. There's no symmetry to this, so it's just 1x. The length, 7, and the height, dy. All right. Limits of integration, 0 to 2. Sub 4, pull that out, 0 to 2, 4 minus y. Subbing for x, what's the equation? Subbing for x involves finding the equation of this boundary line. What's the equation of this boundary line? Y equals 4/3 x. So solve for x, then x is 3/4 y. If you did that and calculated correctly, and put joules on it, then you're good to go. Okay? Last but not least, one little wrinkle here. A barrel with radius 0.4 meters and height 1 meter is filled with water. Find the force against the side. Now this one's a little different because it's a circular figure rather than a flat face. So things are going to be a little different. I would suggest you put the origin here at the center of the circle at the bottom. The radius is 0.4 meters, 0.4 in either direction, and the height is 1 meter, and it's filled with water. All right. Let's talk. Actually, you do it. Go A and B. Talk it over with your math amigos, and we'll see. Don't expect, I will say this, just getting you started. Can you expect rectangular sheets here? Or is it going to be a little different kind of slices being pumped out? All right, so different, so expect that. How we doing? Listos? Okay. So for the force, it's kind of funky because it's not one flat side, but out in all sides. But you could think of it as one big unwrapped rectangle with lots of little long, thin slices of area. Yeah? The only difference is that what is the length of this? Circumference. So 2 pi r with radius of 0.4. So this distance is always going to be 0.8 pi dy for the area. So hopefully you did something like this water, 9,800. What'd you say for the depth? 1 minus y, I agree. And for the area, that's the area of this slice against the outside of the container, so that's 0.8 pi dy. From where to where? 0 to 1. Do you win? I win. All right. So, how about the work? Did you say something like this to start with? And rho is 9,800. The distance, what's the distance you have to pump fluid? 1 minus y. You can see when it's filled, the top of the container and the top of the fluid are the same. So these can be the same in those cases where it's full. What about the volume? Yeah, pi r squared h for the volume of a cylinder. Radius is constantly 0.4. You could put out front. It needs to be squared. The height is dy, and it's still from 0 to 1. Okay? Are we doing okay? Cool. In his infinite wisdom, Saxon gave a really tough, geometrically hard problem in number 4. So would you go to box 4 in the homework and just get the picture, please. It says this is an isosceles right triangle. So you have it looks better on my computer. That doesn't look like a right angle. This is still stretched, okay? So if you were to place the origin at the bottom here, let's start here. If this is a right triangle, what's the hypotenuse? And it's isosceles, sorry, isosceles right triangle. What is that? 5 root 2. It is 5 root 2. That means that this whole thing is 5 root 2. So this guy is 5 root 2 over 2 for half. And if it's isosceles, then these are the same. So would you say that the height is 5 root 2 over 2? With that picture, the work and force part will go better. But the geometry was the sticking point for students, and I don't want you to get stuck on the geometry. I want you to focus on the practice. All right? That's it. Let's see. Should we hand out tests or should we go over questions? We're definitely not going to have time to go over it, but you can see how you did. All right. Let me record a few more. I would be most grateful if you don't cry. I don't want to make you cry. It makes me so bad. So don't cry. I need these back. Will you take the phone off your desk, please? No phones. This was They're going to slip some steps. There's the other page. I'm sure I'll have time to go over it a little tomorrow. Is there anything you'd like to ask about right now? Actually, should we just start going over it a little bit? Okay, so here we go. Feel free to write yourself notes. You may study these later. It might just help you remember by writing it down. So number 1 was the same for both versions. Actually, I should stop recording this.